The Titration Lab, we're using this apparatus to titrate an acid and a base. I won't say which one we're titrating with which, but one of them is the titrant, that's the one we know. The other one is the unknown. We are using kind of an oddball acid, oxalic acid, kind of shaped like an X, like the name implies. The thing about oxalic acid is it's got 2 protons. Oops, that makes it what we call diprotic. Can give off 2 protons. So it's kind of an extra acid, kind of like sulfuric acid can give off 2 protons. Acids like hydrochloric cannot, even nitric cannot, even acetic cannot. So this makes it diprotic. These 2 are diprotic. They can give off both of their hydrogen. Okay. We are neutralizing. We're going to put them in until we reach the equivalence point. The equivalence point is right at pH 7. We're going to get as close to that as we can. Okay, when we put in the reactants, oxalic acid and sodium hydroxide. Oh yeah, by the way, sodium hydroxide is the very epitome of a base, the perfect little base. It doesn't produce 2 hydroxides, just 1. Okay? And then we get the products. Well, the way we usually write them, we leave out the hydroxide, we leave out the hydronium that forms. Okay, we don't talk about that as much. The products wind up being disodium oxalate and water. And when you get there, you don't have any more acid or base, so the pH should be 7. It's a neutral solution. How are we going to know when we're at pH 7? Well, we won't exactly, but when we're at pH 8, phenolphthalein shows up. I think it shows up a little before that, just beyond 7, when it's a very faint color. I think you're actually very close to 7. We've done tests in our labs to show that you're extremely close to that. So we'll know we're near the equivalence point, basically when it turns pink. If it turns dark purple, well then you could be anywhere up here. So it's hard to say where, but if it's a faint pink, you know you're very, very close, within a tiny fraction of a milliliter of the titrated point. And in that situation, your moles of hydronium and your moles of hydroxide are matching up. They're taking each other out in equal concentrations, like if I make a hydronium and a hydroxide like this, hydronium and hydroxide, whoosh, now we got 2 waters. It's the opposite of the self-ionization of water. It's the self-deionization of water, so to speak. That is a neutralization reaction. So notice all neutralizations are the same reaction. Hydronium and hydroxide producing just water. The way we write it, well, we leave in the other ions, it looks different. But that's what's really happening. That's what has to match. And you don't get rid of all of them because water always produces some, so you're always going to have a background rate of 1.0 times 10 to the minus 7 molarity concentration of both of these guys, which, by the way, is not very much. It's a small amount in a neutralized solution. Conductivity, well, we're going to check the conductivity of a base because we haven't checked that yet. I wonder if they're as good as acids. I wonder if there even are electrolytes. You can probably guess, but do you think they'll be as good as acids that make this? Something about this is special. Once again, the acid is called oxalic acid. It's a diprotic acid. It makes twice as many hydronium as a typical acid does. We won't talk too much about whether they all dissociate. You'll maybe discover that in the lab, or we'll discuss that later. Okay, the titration lab. The first few steps are about cleaning your apparatus. So this is the burette, this tall, skinny instrument. It's one of the most accurate volumetric instruments we have. It's even more accurate than this skinny guy, okay? And you can regulate the flow. So what I'm going to do to start cleaning it out is I'm going to dump a little bit of water in, and it's going to pour through. It's going to pour through, well, the valve open, which is in line with the burette. It's going to pour through into a waste beaker, That's to flush out, let's say there was some kind of acid in there, or something that wasn't supposed to be in there. The only problem is, now it's contaminated with water. It's very hard to get every single bit out of a burette. There's going to be a trace amount at the bottom. So what I actually want to do is flush it with a very tiny amount. Notice I'm not really measuring this, but it says about 2 milliliters, very, very little, like a splash. And now I'm rinsing out the water. That's sodium hydroxide, so then the water is being flushed out, so we don't have to worry about water as a contaminant. Now I've cleaned my apparatus. I want to close the valve. I want to add the sodium hydroxide. It's going to skyrocket up as I pour it. As I pour it up here, I'm going to pour it in, and notice the level shoots up very quickly. I'm pouring so slowly, by the way. So slowly, much slower than you would expect to have to pour it, because volumes are deceptive and this is a very skinny instrument. I'm going to have to focus more on what I'm doing pouring than on the camera to get it just right. I want to get it 11, 10, 9, 8. I get it just above the 0. Notice that burettes are labeled upside down because they measure just above the 0. Okay? They measure how much you've poured out. Now if I turn this very carefully, I might be able to get it right on the 0. Okay, if I don't, it's not a big deal. Oh, I think I nailed it, right on the 0. The bottom of the meniscus, the bottom of the bowl, resting on the 0, that's a good place to start. And then I can record that on the back of my lab as my initial volume of 0.0. My final volume will be wherever it stops. And then because I'm starting at 0, it saves me a subtraction. These two will be the same. Okay. I'm going to measure out my acid directly into the flask to cut out the middleman. I'm going to 0 the mass of the flask so that it's ignoring the glass. And I have to very carefully add this so I don't overshoot it. That's the problem. I'm going for 0.47. Oops, I better go very slowly now. I'm sprinkling it in little by little. 3.8, 4.7. Oh my gosh. 4.7, 4.8, 4.7. Boom. Got it. So now I'm going to add my distilled water to my flask. Now technically I'm supposed to add it until the total volume reaches 100. Right now, to save time, I'm pouring in 100 milliliters, but if I wanted this to be accurate molarity, then I would actually pour it in until it reaches 100, because it's actually the volume of solution, not the volume of solvent, right? Now this is what Erlenmeyer flasks are great for. We just call it a flask, because this is the one we use the most. It stirs things up without a stirring rod. You don't want to use stirring rods if you don't have to. It's only going to take little chunks away and mess with your results. The one important thing is don't forget to add the indicator, phenolphthalein, okay? Make sure to add the indicator. So I put in 0.47 of acid, and it says to add 4 drops of phenolphthalein. So I'm gonna go ahead and do that. 1, 2, 3, 4. That was 4. Okay, the good thing about that is now it'll show if there's a base. Doesn't look like it's showing anything. It's hard to tell without a white background. That's why we have this white background right here to tell, but oh, it's not a base. It is an acid. How can we tell if something's a base? Well, got blue litmus paper. Does that show a base? Well, sodium hydroxide doesn't change it. No, that actually shows you when you have an acid, doesn't it? Red litmus paper, we haven't seen a result before this lab. Dip that in. Oh, that's pretty clear. That changed. That's what we call blue, even though it's purple. That means this is a base, okay? Phenolphthalein is similar. It shows up at pH 8, but it's a liquid indicator, and it will show up in our solution. So now I'm going to slowly start adding small amounts, and we will see splashes of color in here. Now at first, I'm being reckless here. I shouldn't probably be pouring it this fast. I just want you to see the color disappearing rapidly, okay? The focus is an issue with this camera. Notice every time I add a splash and stop it, it disappears. When I turn my valve, I line it up, and shut it off. I can regulate it down to a low level, so it's just a trickle or just drops falling in like this. And you can see each drop is making a splash because right where it lands, well, of course, this is base in the burette. This is sodium hydroxide. We just saw that it's a base. So right where it lands, that's going to be a base. However, the base is quickly neutralized. Okay, even if you dissolve the base throughout the solution, the overall solution remains an acid for quite a while. You have to get rid of 90% of that acid before you change 1 pH. Okay, so I've been adding little by little. I've been adding it, and it's turning color. Notice the color disappears. I can make it go faster like magic if I do that. Okay, by swirling it around, it helps it neutralize it faster by contacting more hydronium. Okay, I can see I've got a ways to go though because it's disappearing quickly. So I'm going to be a little bit reckless here. I have some idea where the titration point is going to be for this. Normally, I would tell students to go exceptionally slow. Okay, but I have a little bit of prior knowledge here, so I'm going to be a little reckless and get closer to the titration point. Okay, you can do that, by the way, on your second attempt when you repeat it with half as much. You can go a little faster too, because you have a rough idea about where it's going to happen, so you can just slow down as you approach that point. You can also tell when the color lasts longer. Notice how it's still fading relatively quickly. When it lasts for a while, you know you're close to the titration point. Okay, what you want to get is the faintest color remaining in your solution. Okay, notice each time I add one, I want to make it disappear. Okay, what I might want to start doing is on the margin of my paper, marking down the volumes. Let's see, 33.9. I can be that accurate, milliliters. Okay, burettes measure how much they've poured out. So that means I've poured in to here 33.9 milliliters of my base. Okay, I'm going to keep adding, keep swirling, adding, swirling. Oh. Uh-oh. See, notice the color is getting a little more persistent. When the color persists for longer, you got to go slower. Looks like a little hurricane in there, a little vortex. Okay, kind of like a galaxy, actually. Oh, and it still disappears. It looked like that might have stayed. So now I'm going very slow. I think I'm pretty close. Splash. That was just a little drop. Ooh, notice how that filled the whole thing before it disappeared? I'm going to go drop at a time now. Drop, drop. Okay. I don't want that drop to miss. It's going to fall in. Okay. Oh! Getting very, very close. Oops, I got it 2 drops. Sometimes it's hard to get an individual drop, but that's what I'm going for here. The reason this is because once you've changed 1 pH, the next change happens 10 times faster. The change after that happens 100 times faster, and the next one is 1,000 times faster. Eventually you're getting to the point where you can change the pH with less than a milliliter. Let's say a drop or a couple of drops, you could change a pH. Okay, remember pH is logarithmic. Oops. And I'm a little bit excited here. I should be going a little slower. Ooh, that was very, very close. That color looked like it was going to stay. I'm going to add drop. And that drop better fall into there. I don't want to lose a drop, okay, because that will mess up my readings a little bit. I'll just swirl it around. Looks like that was going to stay, but let me write down the volume again. Let me cross out the previous one, 33.9. Now we're at 37.123. I'm going to cross out the 33.9, write 37.3, because I think I'm right on the verge. Let's say I overshoot it, then I can get a boundary. I know it's in between 2 numbers. Okay? I think it's going to happen with just a couple more drops. Because it's not lasting a very long time. Ooh, look at that. Look at that. Faint pink. Faint pink that's almost persisting. So this part takes a little bit of time, so you got to be patient. Very easy to overshoot it. Oop. Very easy to add too much. There's a lot of things that could go wrong here. And I've got a faint pink color that's taking a while to fade. Notice how long that took to disappear. That's why I have this white background, because it would be hard to notice that faint color without a white background. I'm going to try to add individual drops now. I'm going to be a little bit more careful than I have been on this, because I was trying to make this video a little faster. That swirl spreads out. Let me make sure the next drop doesn't fall in. I want the next drop. Is it going to persist? Taking a while. It's taking a while. That might remain. It's still slightly pink. It's still slightly pink. Nope, it disappeared. So I know I'm very close. The more patient I am, the more exact I can be. The thing is, if I get it exactly, then I'll get the concentration calculation more exact. Okay, the pink color is lasting. It's lasting for several seconds before fading. So I don't want to add more than a drop at a time now. Okay? More than a drop. And that could be it. If that doesn't disappear, then I've reached the equivalence point. I think I might be there. If that color remains and doesn't disappear, I see a faint pink color, maybe you can see it. If that doesn't disappear, then I've reached the equivalence point, meaning that the same number of hydronium that were added by the acid, that powder that I put in, are neutralized by the same number of hydroxide from the base. This is extremely faint. And I'm going to write down the volume now, because I think the color is still there, even though it's hard to see looking at the white background. It doesn't quite look clear, very close. So I'm writing down the volume. I think this should be my final volume, 37.8. 37.8. Notice the last time I stopped was 37.3. I thought I was there. I only added half a milliliter since then. I'll know if I was there if the next one becomes very visible. If I add another drop and it is much more visible, then I'll know that I was really there. If it doesn't, well, maybe I was mistaken. It's possible that I'm just seeing things, seeing colors. So you got to be careful to double check, but don't forget to write that down first. If I didn't record that, I wouldn't have the most accurate measurement for my titration. So the faint pink color appears to remain. I'll watch it for a little while. If it does remain indeed, then it's 37.8. I'm going to just show you if this is correct. I'm going to write it in. 37.8 milliliters is my final volume. And then 37.8 minus 0 is the same number. 37.8 is my titrated volume. I could try this again with half the number of grams of oxalic acid, which winds up being half the concentration. And then I know that it should take half as much as this to neutralize it. Half as much sodium hydroxide. So divide this number by 2. If I divide one number by 2, the other one should be divided by 2. And look, it's still there. This was it. So I did titrate this almost exactly. I would say the first number was better than this. I think I was there at the 37.8. Now that I've added that drop, it is 37. It hasn't really moved much. Still about 37.85, I would say. I could split those. You can actually split the lines, interpolate. But I think the first number was more accurate when it was barely visible. I was correct. It was there. So that was almost a perfect titration of oxalic acid using sodium hydroxide. One of them was the titrant. One of them was the unknown. You're going to have to figure out which one is which. Let's check the conductivities of the various species. Here is my acid. Okay, it's showing low 3, high. It's not showing high, so low 3. Let me rinse off the electrodes to make sure there's no contamination. I'm just going to try wiping these off to get as much as possible up there, because of course one thing could affect the other. Okay, the next one I'm going to look at is my neutralized solution. Let's see what that is. Does that contain electrolytes? That is low 2. And does it give me a high reading? No. Okay, then I'm going to wipe off the electrodes once again. Okay, and I'm going to try the base. Let's look at the base, which is in here. Okay, that's low 3. What about high? Okay, so notice that all three are electrolytes, contain electrolytes. You should understand why. One that I did not put in there, it's hard to keep it pure, but I'll put in some distilled water. Pour it in that one. And again, if my electrodes are kind of clean, we'll see if the distilled water shows anything. The problem is keeping it distilled is very hard. This might not be perfectly clean. And it doesn't show anything. Interesting, good. I must have cleaned those electrodes. So distilled water doesn't show low, doesn't show high, just like we're supposed to see. So this was a good result. Sometimes you get contamination if it's not a clean well plate, or if you have something on the electrodes and the distilled water will show, but as you can see here, distilled water does not contain electrolytes, or at least not enough to light it up. So I'm going to check my neutralized solution, my very faint pink solution, just to make sure. Okay, this is the blue litmus paper. Does that change? No, interesting. Here's the red litmus paper. Does that change? No, that must be neutralized. If neither one changes, the only time that neither one changes is when you're very close to pH 7. Remember, litmus paper is a very simple test. It's made out of lichen. It reacts with acids and bases. Okay, it either shows up or it doesn't. That's why they call it a litmus test. So you should be able to tell if it changes. It doesn't just get darker wet like that. You can check that compared to distilled water. It looks the same as this. So we really did a good job of neutralizing this one.